Okay, we're going to find the slope of the tangent line to this function at the point 2, 1. And we're going to use implicit differentiation to do so. So this is a little bit of a tricky one, but as we get going on it, we're going to go one term at a time and kind of take derivatives based on each one individually. So the x squared, its derivative is going to go as 2x, just using the power rule, and that could get a dx over next to it. I'm going to ignore that for right now and only put a y prime or dy dx whenever we're taking the derivative of a term that has a y. So I'm looking over here, here's a y, and here's a y, so we want to be careful of each one of those. All right, for that middle term, I'm going to treat this as negative 3x multiplied by y. Because we have two different variables in there, I want to be very, very careful as I do this, that they're being multiplied together. So the first term I'm going to treat as f, and the second one, and I shouldn't call them different terms, I'm going to treat negative 3x, that first part of that single term, as my function f, and the second part is going to be y. I'm going to treat that as g. So because these are two things multiplied together, I'm going to use the product rule. So f prime times g plus f times g prime. All right, so in taking the derivative of what I'm calling f, that negative 3x, its derivative is going to be negative 3, and I don't put a dx next to it, times, I'm going to copy down g, which in our case I'm treating as y, the second half of that term, plus, now I copy down the f, so negative 3x multiplied by the derivative of g is, the derivative of y is just going to be 1, but this time I want to put a y prime next to it because our variable was y. All right, moving on to that last term on the left-hand side, the 7y, its derivative is going to be 7, but remember our variable was y, so we need to put a y prime next to it. Now, if this is the first example you've seen that had multiple y's involved, just be careful as you go through it. Every time you take a derivative of a term that has y, or what we're treating as a function with y, you have to put a y prime or a dy dx next to that. Over on the right-hand side, the derivative of a constant is always going to be 0. All right, now as we take a look, we have a y prime here and another y prime here. Our end goal is to get that y prime on one side all by itself. So what I'm going to do is start moving terms away from that. It's a little tough to see. It seems a little bit like we've got a lot going on in this problem right now. But the terms that don't have y prime, I'm going to move those to the other side. So like the 2x, let's move it to the other side. Those are going to go away, make 0. We have negative 3y minus 3xy prime plus 7y prime equals negative 2x. Now it's getting a little bit clearer. It looked a bit messy up on that first line. But now I still want to get the y primes on one side, so let's move that 3x to the other side, or sorry, 3y to the other side. So we'll add that, move it over. That'll leave us with negative 3x y prime plus 7y prime equals, you can put these in either order. I'm going to go 3y minus 2x. Okay, from here, I still need to get y prime all by itself. So we're going to use that technique where we factor out a common factor. Both of these terms that are left on the left-hand side both have a y prime. So if we remove that, we're going to be left with negative 3x plus 7 inside our set of parentheses. We could redistribute and get those same two terms back if we wanted to. All right, to finish this up, we need to get y prime all by itself, but it's multiplied by this big set of parentheses. Let's go ahead and divide both sides by negative 3x plus 7. All right, and that'll put y prime on the left-hand side all by itself. Equivalently, we could use Leibniz notation, dy dx, to indicate the derivative. All right, so that's how we can write out the formula for it. But on our specific example, we were told this point is where we care about that slope of the tangent line. So we found the derivative using implicit differentiation. Now we're going to use the x value of 2 and the y value of 1 and plug those into our formula. So x value of 2, y value of 1. So 3 times 1 minus 2 times 2, negative 3 times 2 plus 7. And a little bit of reducing down and we'll have our slope. Right? 3 minus 4 over negative 6 plus 7. I got this to be negative 1 over 1. Works out to be negative 1 for the slope of the tangent line at that point. So I hope this helps out as you're working on implicit differentiation. I know as you're first getting started, it feels a little bit confusing using all these derivative rules, but just be careful. If you ever have a y and you're taking the derivative of that part, you have to put a y prime as part of your implicit differentiation, or a dy dx. All right, good luck.